Welcome back. So in our previous video, we learned about unitary transformation and two quantum logic gates, that is the C naught gate and the swap gate. Now in this video, we will transport or send a quantum state from one point in space to another point in space. This is referred to as the quantum teleportation. So quantum teleportation is a technique for sending a quantum state from one point in space to another. Now imagine the following diagram. There are three channels. The first one is the unknown qubit state psi, and 2 and 3 are together, that is a different state. You perform a C naught gate on the first and the second qubit, do a Hadamard transform on the first, make measurements, then appropriately apply X or Z gate, and at the last you would recover the state that was in the channel 1 would be transmitted to channel 3. So the first qubit, let us say, is possessed by Alice, and the second qubit is possessed by Alice, which is entangled with the third qubit possessed by Bob. So let me go back to the previous slide to tell you that the first and the second qubit are held by Alice, and the third one is held by Bob. The second and third qubits are entangled states. One part is with Alice and the second part is with Bob. Alice needs to send the qubit ket psi, which is an unknown quantum state. A and B are not known. A ket 0 plus B ket 1 to Bob, who is spatially separated, who is a very long distance away. So the state ket B beta 0 0 that is shared between Alice and Bob is this entangled state. Ket 0 0 is equal to 1 by root 2 ket 0 plus ket 1. So the first part is with Alice and the second qubit is with Bob. So the input state to the circuit is psi 0, which is the product of these two, which is ket psi into ket beta 0 0. So multiplying, this is what one would get: 1 by root 2 A 0 0 0 plus A 0 1 1 plus B 1 0 0 plus B 1 1 1. Now going back to the diagram, you can see once this is done, once you have the state psi 0, the next operation to obtain the state psi 1 is to perform a C naught gate, with the first qubit being the control and the second being the target. So do a C naught transformation wherever necessary. So wherever the first qubit is 0, you don't have to do anything. Whenever the first qubit is 1, flip the second qubit. If it is 0, make it 1. If it is 1, make it 0. So this is the state psi 1. So this is followed by a Hadamard transformation on the first qubit. So the Hadamard transform transforms the state 0 to 0 plus 1 by root 2 and the state 1 to 1 minus 0 minus 1 by root 2. Simplifying, this is what one would get. So see the second equation for psi 2, 1 by 2 ket 0 into A 0 plus B1. So that is what Bob holds. The first two qubits are with Alice, plus 0 1, which Alice has, into A1 plus B0 plus 1 by 2 1 0 A0 minus B1 plus 1 1 A1 minus B0. So the one within the brackets are the state possessed by Bob. The first and the second qubits are with Alice. Alice has to make measurements on the first and the second qubits. After measuring the state psi 2, she will get one of the possible states. She would either get 0 0, 0 1, 1 0, and 1 1. Alice has to make a phone call to Bob and tell him which state she got. If Alice gets 0 0, she should tell Bob to apply an identity gate to his qubit. Because if you see here, for the state 0 0, you already have the state A0 plus B1 for Bob. So he need not do anything. That is the state psi. So he has to apply identity channel. So if Alice gets 1 0 on her measurements, Bob has to interchange 1 to 0 and 0 to 1, which is done by applying X gate. So Bob has to apply X gate. If Alice gets 1 0, then Bob has to apply Z gate, because if Alice gets 1 0, Bob has A0 minus B1, so the minus 1 has to go to plus 1, which is done by applying the Z gate. And if Alice gets 1 1, she should tell Bob to apply X gate followed by Z gate. First, when you apply X gate, 1 becomes 0 and 0 becomes 1, and the minus sign has to go away, so apply the Z gate. So after Bob applies the appropriate quantum gate to his qubit, he has obtained the qubit psi A0 plus B1, which was possessed by Alice. Hence, Alice has successfully teleported the qubit to Bob, who is spatially separated. So in 1999, Anton Zeilinger and his team did quantum teleportation for a few kilometers apart experimentally. Here I would like to mention there is no faster than light communication, because Alice has to make a phone call to Bob and tell him what are the measurements that she got. So this would not violate any kind of faster than light communication. It is only that the quantum state that Alice had is now with Bob. So these are the references used and the suggested reading for quantum computation. Quantum Computation and Quantum Information by Nielsen and Chuang. Quantum Optics. The end chapter has a chapter on quantum communication by Mark Fox, and a brief note on quantum computation has also been mentioned in the book Physics for Engineers by M.R. Srinivasan. So this was just an introductory course on quantum computation, specially meant for undergraduate students. Thank you.